Hello everyone, I am Andres Aristizabal. I am a physicist and an electrical engineer. Welcome to my science and engineering channel. Today I will teach you to apply the iterative method of the fixed point. Let's start. We are going to define what is an iterative method. It is a process to solve a mathematical problem such as an equation or a system of equations, using successive approximations starting from an initial estimate. And why are iterative methods practical? They help solve problems involving many variables, sometimes on the order of millions, where direct methods cannot be used, even with the power of the best computer. Now, let's define a couple of very useful concepts for numerical methods. What is tolerance? When numerical methods are used to obtain the approximate solution to a problem, it must be within a range that we consider appropriate and that we call tolerance. What is convergence? Convergence of a numerical method is understood as the guarantee that when a good number of iterations are carried out, the approximations obtained end up getting closer and closer to the actual value sought. To the extent that a numerical method requires fewer iterations than another to get closer to the desired value, it is said to have a faster convergence. Not all numerical methods converge. On the contrary, they diverge. They move farther and farther away from the desired result. It is then said that it does not have good stability. Okay, so now let's define the iterative method of the fixed point. Let f be a continuous function on the interval a, b, and we take into account that we want to obtain the solution of our equation f of x is equal to 0. So, if we manage to replace that function with another that is of the form x is equal to g of x, then alpha is the root of both if and only if alpha is a fixed point of g of x. That is, it satisfies alpha is equal to g of alpha. How this translates into the fixed point theorem? Well, let's define it. Let g be a function on the interval a, b, which is continuous and differentiable in that interval, but with the condition that its derivative is bounded with a value less than 1 for all values of x belonging to the interval. Given x0 in the interval, then if we calculate the sequence of xn is equal to g of xn minus 1, we will find that it is convergent. Therefore, alpha is the root of the equation x is equal to g of x. Well, now let's see an example to understand this method. Let's solve this equation. X cubed plus x is equal to 6. The first thing we have to do is set the equation equal to 0. Then it is as follows. X cubed plus x minus 6 is equal to 0. And I am going to define below the steps to apply the method. Step 1. We find the confidence interval. Then we build a table of x versus f of x. Next, we assign values to x from minus 5 to 5, and we get these values for f of x. Then we have to identify when f of x changes from a negative to a positive sign. In this case, the change happens when x is equal to 1 and 2, obtaining f of x is equal to minus 4 and to 4 respectively. So that will be our confidence interval. We then obtain the midpoint by calculating 1 plus 2 divided by 2 and this is equal to 1.5. This value is the midpoint with which we are going to work. Okay, so what is step 2? We have to find all the possible clearances of x from our original equation. So over here we have our original equation, and the first variable that we are going to isolate is x cubed, that is in red. Then x cubed is equal to minus x plus 6. After that we write g of x is equal to cube root of 6 minus x, which is the same as writing 6 minus x raised 1/3. Now we make the following available clearance of our equation, which is x. We isolate x and we write g of x is equal to 6 minus x cubed, as it appears here in green. We go now with step number 3. We take each clearance and derive it. So over here we have the first clearance of g of x is equal to 6 minus x raised to 1/3, and we do the derivative and we obtain minus 1 divided by 3 times 6 minus x raised to 2/3. Now I take the other clearance obtained in the previous step. G of x is equal to 6 minus x cubed, and we derive it and we obtain minus 3x squared. Then we apply step 4. We replace the midpoint of the confidence interval and the one that fulfills that its derivative is between minus 1 and 1, then it will be able to iterate. So we rewrite the midpoint, our midpoint 1.5, and rewrite the previous derivative. We make the replacement with the value 1.5 and we obtain minus 0.1229, and since this result meets this requirement, then it is suitable for iteration. We rewrite the other derivative that was minus 3x squared, and we replace x by 1.5 and we obtain minus 6.75. Since this result does not meet this requirement, then it is not suitable for iteration. We now go to step 5, which consists of iterate with the clearance that is suitable. We rewrite the equation of our derivative, and now g of x is going to be equal to 6 minus 1.5 raised to 1/3. Then I build the iteration table that appears here. The first thing we have to calculate is this column g of x. We get this first value when we replace the midpoint 1.5 here in this equation, and we get 1.6509, and I write that value here. Then I replace that same value 1.6509 here in this equation, and we obtain the next value of 1.6322, and in that way I successively make the replacements to obtain the subsequent points. For the column of x, the first value is our midpoint 1.5. The next value will be the number of g of x. For the next value, we take the 1 after g of x, and so we continue for the other values of x. In this column, we have the sequence. How do we obtain it? We set the first value to 0, as you can see here. The next value is obtained by subtracting 1.6322 minus the previous 1.6509, and we obtain minus 0.0186. Okay, so successively we obtain the following values, and when our sequence reaches the value of 0, its corresponding value of x, this one, 1.6346, will be our fixed point. Now we go to the final step, step 6, which consists of replacing our fixed point in the original equation. So here we have our original equation. We replace our midpoint and we get 6 is equal to 6. And then in this way we have solved our equation by applying the fixed point method. Okay, that's all for now. Thank you very much for your attention and see you another time. Bye.